obtained his Bachelor of Science in Physics in 2013, then obtained his Master of Science in Particle Physics and Nuclear Physics in 2016. After that, he joined NGIT as a PhD student and obtained his Applied Physics degree in 2023. So in NGIT, Yuqian is participating in upgrading expanded Owen 3D solar array to EOSA 15. And he is also exploring the application of deep learning methods in radio interferometry imagery reconstruction. Yuqian's research interest also includes radio images, statistical data analysis, software development, and continue on the observational studies of the energy release and corona magnetometry, utilizing data from EOSA combined with multi-wavelength observation. So today Yuqian is going to talk about giant microwave and X-ray observations of superalgidontals impacting the rooftop and above the rooftop regions. So Yuqian, please take it away.
Thank you very much. Thank you for having me here, and I'm glad to have this great opportunity to give an introduction to our very recent work. All right, so like Sharon said, I'm from a solar physics group, so people love solar flares, and it's very energetic, and it's the most violent energy release in the solar system. So here is an example. It's not the biggest one, but it's definitely the most beautiful and standard one during, I'll say, last 2 decades. So it's a X8.2 flare, occurs on 2017 September 10. The reason I call it standard or beautiful is it looks so much similar to the standard model. So the standard model is the most well accepted model, also known as the SKP model. So the model describes the solar flare start with magnetic reconnection, and there will be many formats of energy released during this process, like the point flux and the bulk kinetic flux, and also the accelerated particles. The reason I think accelerated particles is kind of interesting and special is because it plays a very important role in the energy transportation in the solar flares, and that's the critical reason that you can observe solar flare features at different heights with different frequencies. And another important thing is about the chronomagnetic field. Why is that? So there are many energy is released during solar flares, but where are those energy come from? So the answer is it comes from the free magnetic energy stored in the chronomagnetic field, and according to a recent study, so the author shows that the free magnetic energy stored in the solar magnetic field is enough to power the whole solar flare. So we have 2 keywords, the accelerated particles and the chronomagnetic field, and that's why the solar radio people love microwave observation. So here is an example of the microwave observation of solar flares. So the observation you are looking at, those colored contours, are the imaging spectroscopy from microwave emission, and the red are the low frequencies, and the blue are high frequencies. So the good thing about the imaging spectroscopy is that you can get a spatially resolved distribution of each parameters, including the magnetic field strength, the non-thermal electron density, and the energy distribution parameters like the power law index or something like that. So basically, if we look at the panel C, we can see that there are 6 spectra are fitted at those 6 points. So for each point, we can get those parameters. So why does microwave observation has such a capability of doing this? It's because during the solar flare, the gyrosynchrotron is the dominant mechanism of the microwave emission. So it's basically the non-thermal electron gyrating the magnetic field lines. So this is why the non-thermal electron and the magnetic field comes together. And this movie shows how does the parameter change the shape of spectrum of gyrosynchrotron. So in this spectrum, the x-axis is frequency in gigahertz, and the y-axis is brightness, temperature, or flux density. All right. So here is our instrument, the YAVSA, Expanded Owens Valley Solar Array. So it's a solar dedicated array at overall the Owens Valley Radio Observatory. So it's like 5 hours from LA, and it's in the middle of desert, like other radio observatories. So because it's a solar dedicated array, so our main antennas, as shown in this figure, is very small. It's actually just 2 meters because sun is such a strong radio source. But for the purpose of calibration, we also have a big guy over here at the corner. So this is a 27-meter antennas used for calibration. So it's observed the relatively weak astronomy source. All right, so other than the impulsive phase of solar flare, and of course there are many phases of solar flares. So YAVSA has many studies within the other phases. So today I'm going to report a study or a phenomena which is closely related to the gradual phase of the solar flare, the superarctic downflow. So the superarctic downflow, as shown in this, oh well, sorry, my computer frozen. There should be a fancy movie on the left-hand side. Okay, sorry, it's not responding. Okay, I'll blame Siji. I think this movie is way too fancy for my computer. Wait, let me try to unplug. Sorry about that. Yeah. Sorry, it's completely frozen. Let me try to reboot. This is a pretty recent one. It's only 3 years old. Oh, here we go. Oh.
We should try this one.
Right. Try to skip the movie. Goes to the interesting part. Director.
Yeah. Yeah. Yeah, this is a fancy movie from my colleague Sijie, and hopefully the movie is worth waiting. So, superconducting downflow. All right. So, as the movie suggested, the superconducting downflow is actually this dark finger-like features, and on the right-hand side is the still version of superconducting downflow. So you can see this black voids, the finger-like structure are the superconducting downflow. So what we know about the superconducting downflow is that the image measure or the density within the black void is quite low, but the temperature is only slightly lower than the surrounding superconducting band region and a little bit higher than background corona. So there are two very intuitive questions about superconducting downflow. How does it originate? So there are many theories about them, but now I show only two popular ones. So the first one comes from Chen Cai's paper, and so it comes from the combination of RTI and RMI instabilities, and so you can also observe something similar in the supernova remain, the post-shock region. And another theory about superconducting downflow, the popular one, is the superconducting downflow is actually the shrinking loops. And it's the wake or the trail of the shrinking loops. So these are the two popular theories about the superconducting downflow. And then another question is, what do they do, or what are they associated with? So here are a few examples showing what do they do. And there are many studies has reported the heating, the adiabatic heating and the viscous heating comes from the superconducting downflow. And from another research, it shows when the superconducting downflow collect the loop top, it will cause this X-ray enhancement. So there will be the so-called quasi-periodic position, the QPP, in X-ray light curve. And of course, the interaction between the loop top and superconducting downflow will also cause the kink oscillation of the flare loop. So, but these are all in the thermal domain. How about the non-thermal domain? So on the left-hand side, there's a simulation work from Xiaocan Li, and which shows that the existing of superconducting downflow in the superconducting fan region will cause the turbulence, and which might help to accelerate or trap the non-thermal electron. And on the right-hand side is actually the only clear non-thermal phenomena associated with the superconducting downflow. So this study shows that the microwave and hardest ray emissions from Nobayama and the RASI are closely associated with the superconducting downflow, but this study doesn't show any like the spatial correlation or the spectral information or something like that. So this is what this study is going to solve. So this is our study co-observed by YAFSA and a satellite solar orbiter. So solar orbiter provide the X-ray image on board the sticks provide X-ray images on board solar orbiter, and our instrument YAFSA provide microwave spectroscopy, imaging spectroscopy. And so in this study, we are going to relate three things. The first thing is the arrival of the size. And the second thing is the plasma dynamics. And the third thing is the microwave emission enhancement. So we are select three observables for these three things. And there are, first one is the arrival of the size. So in this figure, we show the velocity field of the size. And we can use this to show the arrival of the size, because the size will cause the compression in front of it. So we can select a certain region and measure the compression caused by the size to represent the arrival of the size. Another observable is the microwave source displacement, because we have microwave image with a pretty good temporal resolution. So in this case, we use 2 seconds, but YALSA can do up to 1 second. So it's a very good. So it's very good at capturing those very dynamic process during the solar flares. So this is how we get the microwave source displacement. And the third one is, of course, the microwave light curve and spectrum. Something special about this is because even though we have a spatially resolved spectrum, but in this case, we have oscillating source. So in that case, we have to fit the whole source into a main source and the secondary source. As you can see in this figure, so the secondary source is most spatially related to the SAS itself. So we can compare the response of the secondary source and the main source to the SAS to see which one has more response to size. So we know that size can cause something. So this is our 3 observables, and here is some results, shows the relation between 2 of them. The first relation is between the SAS arrival and the plasma dynamic. So basically, we can see each time there is a size arrived, represented by this purple light curve in the lower panel, there is a microwave source displacement. I think the one-to-one correlation is very clear, and so the SAS comes to this way, and there will be a source displacement occurs here. And the next, and we also find out that this secondary source is the displacement of the secondary source is about 10 seconds ahead of the displacement of the main source, which means the perturbation is propagating from downward to the upward. So we review the process of propagation of the source displacement. And another relation we want to build is the microwave source displacement and the light curve, which is the microwave emission enhancement. So we find out that the microwave source displacement and the secondary source and the light curve of secondary source has a very good one-to-one correlation, as you can see here. So the middle panel is the overall microwave source displacement, and at the lower panel is the corresponding secondary source light curve. So you can see a very good one-to-one correlation there, but as to the main source, there is no correlation. So we find out that the secondary source has more correlation with the arrival of the size, and it's also more close to the size. So we come to the conclusion that this oscillation comes from the SAS directly. Sorry, so I guess I'm running out of time. Okay, thank you. And so I think I'll skip some of them and goes to the conclusion directly, the interpretation. All right, so here is our interpretation. So as in this cartoon, you can see the SAS is moving downward, propagating downward. And we have 3 observations. The first one, the first thing happened is the microwave source enhancement, because the microwave source is more sensitive to the magnetic field and is a little bit higher than the other sources. And first we have this microwave source enhancement, and then we have the microwave source displacement, because we interpret the displacement as the fast mode magnetic sonic wave, which has a speed of Kelvin speed, and we estimate the speed and is comparable to the Kelvin speed. So this is why we have a 12-second delay between the microwave source displacement and the microwave source enhancement. And 40 seconds after the microwave source enhancement, we have this thermal X-ray source enhancement. So I think this cartoon shows the whole process of downward propagating SAS effect on the microwave source, soft X-ray source. I think this is our main conclusion. So I think this is the first time we reviewed that the size is co-temporal and co-spatial with the enhancement of non-thermal microwave emission. And we also see some hardening spectra. And the microwave emission at different frequencies and X-ray enhancement form a complete time series showing the size moving towards to the sun. And we also reviewed the size can cause some microwave source displacement and propagating at nearly the Kelvin speed. Thank you. I think that's all. That's all from me. Sorry, I skipped some details because of our technical problem.
Any questions? Debbie.
Okay, I might give you an opportunity to talk about the slides you skipped, but I'm wondering if like higher frequency radio, like submillimeter observations would help or would be useful for this kind of project. The reason I'm asking this is we're trying to find some funding to convert the submillimeter array to do solar observations, and so we're always looking for good use cases for it. So if you had, 100 to 400 gigahertz observations, relatively good spatial resolution, would that be useful for your project here?
So for my project here, we're basically observing the gyrosynchrotron emission, and at the loop top region, the magnetic field is generally not that high. And so I guess if we are going to that high frequency, we need a very, very high dynamic range to resolve something like that. Because I know that because ELSA is struggling with the dynamic range, that's why we need phasor. Because if we are still looking at the gyrosynchrotron, we can see the brightness temperature and flux density is going all the way down to those high frequencies. So I guess if we can see something like SAS in that high frequency, we need very, very good dynamic range. I'm sorry. But that's only from the perspective of gyrosynchrotron. I'm not sure about the other emission mechanisms.
Why is there a 40-second delay between the microwave?
The 40 seconds delay basically comes from the height difference between the microwave source and the X-ray source. That's my interpretation. And there is also the so-called the Newpersian heating. So if the heating is caused by the non-thermal electron itself, there will be a delay there. But I think 40 seconds is too long for that. I think the main reason there is a 40 seconds delay is because of the height difference between the microwave source and the X-ray source. So as you can see in the right-hand side panel, so up here is the microwave source, and down here is the soft X-ray source. So there is about 10 arcsecond difference there, and the size, the velocity of size is about 140, 150 kilometers per second, and I think the time difference and height difference agree well with each other. Yeah.
There's another question from Mark. So is there something extra that could be learned from micrometer or sub-micrometer observations, say 1.3 micrometer or 817 micron? And also, what spatial resolution is needed to really make some progress in understanding?
Yeah, I think that's a very good question. I'll go ahead and answer the second part of the question because the first part I really don't have a good answer for that. I'm sorry about that. So about the spatial resolution here, the best you also can do is about 6 or 7 arcseconds at high frequencies. And I think in order to make a good measurement of sets, we need at least about 10 arcseconds or so. So I think that's my answer to it, but I'm not sure about it. Yeah.
So if there's no more questions, thanks, Yuqian. So,
Yeah, I
oh,
have a
please,
question.
sorry,
Yeah.
sorry, I
No,
didn't
it's
say.
fine. So you mentioned about how QVB is not really associated with that. Do you see those QVBs in the gradual phase of the flow or in the impulsive side?
Okay, yeah, that's also a very good question. So this event is a little bit special. It's because in this event we observe this super downflow during the impulsive phase instead of the gradual phase. But during the gradual phase, there are some sets as well. So because of this special event, we can see how does the sets modulate the microwave source during the impulsive phase because when the microwave source is really strong. Yeah, but during the gradual phase, we also see some of those. And in other events, so my colleague is working on, so there is some corresponding like this during the gradual phase as well. So we'll keep working on that.
Are there, follow-up question. How long are the periods? Are there 20 or
There are about 50 seconds. Yes, thank you.
So Yuqian's office is P42. Feel free to stop by or sign up with spreadsheet.
Yeah.
So thank you so much.
Thank you.
That's his name, yeah.
So, it is my pleasure to introduce our second speaker of the day, Stephanie Jarmak. She got her PhD from the University of Central Florida in 2020, and after her postdoc position at Southwest Research Institute, she joined here last year as a planetary science project scientist. So, as her position name suggests, she works on the broad topics of planetary science. And today she's going to talk about the JWST observation of this interesting asteroid. So please take it away.
Okay, great. Do I need a microphone?
Sorry.
Let's see if I can clip this on reasonably. All right, can you hear me? Good? Okay. All right, yes. Thank you for that introduction. My name is Dr. Stephanie Jarmak. So I was hired here at the CfA November 2023 as the project scientist for planetary science for the expansion of the astrophysics data system to the Science Explorer. In part of that role, I dedicate some of my time to planetary science research to make sure that I stay up to date with the field and make sure that we are catering to the needs of planetary scientists. So in that time, I do a wide variety of planetary science research, including granular mechanics modeling, planetary rings, working on mission concept studies, and part of my research is also observing asteroids with remote sensing techniques. My main talk today will provide some motivation about why it's interesting and useful to be able to observe asteroids. And then I'm going to end the talk with some focused discussion about recent observations of the asteroid 16 Psyche with JWST as part of the JWST GEO program 1731 from Cycle 1. Okay. So I would wager most of you, when you think about JWST, you think about something like this, maybe except for Martin Elvis. But I would encourage you, let's start to think of a little bit smaller, even smaller than this, okay? So we're gonna go to the solar system, right? Even though My job title technically has astrophysics in it for the SAO side. Don't be fooled, I am not an astrophysicist. I study planets. And JWST, some people, especially the public, don't really realize that there was a lot of engineering work that went into making sure that space telescope would be very well suited to being able to study the objects within our own solar system. And the objects I'm going to focus on today are located in the asteroid belt. So I don't consider asteroids to be the vermin of the skies, unlike maybe some of you. Maybe because most of my mentors study asteroids, but they're really, these small bodies are really useful to answer some of the biggest questions, like why are we here in terms of how did our solar system form, and to understand that we need to know how the planets formed, and the asteroids represent the remnants of the planet formation process and are thought to be these pristine records for us to understand how our solar system came to be, and we can extend that then to interpretations for solar systems outside of our own. They're also interesting to study in terms of hydration, thought to be the deliverers of water to our planet, and also they are, on the more sort of practical space exploration side, useful for studying in terms of in situ resource utilization, so harnessing their regolith material properties to be able to build up resources, extract water and things like that for future space exploration, essentially. And as much as I adore them, they are a threat, right? So we have to be a little bit concerned with the potential hazard that they pose in terms of colliding with our planet. And so to that end, there was a recent mission that was the DART mission, which basically slammed a spacecraft into this little tiny asteroid moon around another asteroid to see if we could use this sort of projectile technique to be able to deflect the orbit of a small body that would potentially be on a hazardous collision course with Earth, and they showed that we could, and also use JWST to observe some of those outcomes, which is pretty cool. Okay, so why observe them with JWST? Why use this precious telescope time to observe these bodies? Well, as I mentioned before, there was a lot of effort that went into the design of the capabilities of the spacecraft and the instruments to be able to get really useful information about these small bodies. And in the infrared, there are a lot of different molecules that are can't really be studied from the ground, or not really well characterized, mainly because of the Earth's atmosphere causing this blockage exactly where you'd want to be looking for, say, water and things like that. And you get this really unique type of data in terms of these spaxels. So you get spatial and spectral information in the form of this sort of data loaf that I'll talk about a little bit later. So the infrared wavelength, you get unprecedented sort of coverage in terms of a space telescope that's capable of observing this range, not only in the near infrared with NIRSPEC, but also the mid-infrared with MIRI, and there's only a slight overlap with Hubble's current capabilities, and then Spitzer's no longer operating. And you also get credible spatial resolution. So this picture here is with NIRCam, which is the imaging capability on JWST, and then near infrared, and that is an ejecta plume from the super tiny little baby asteroid moon Dimorphos around the asteroid Didymos, and that's the plume that happened after the impact of the DART spacecraft into that object. And this spatial ability is also really useful for any observations that are taken with NIRCam. There's a high probability that there will be unidentified asteroids showing up serendipitously in those observations, and so that can be used to discover new small bodies. Then maybe the galaxy people think those are vermin of the skies, but it's really quite great. You can remove them easily. And then there's really enhanced sensitivity, so we have resolving power of several orders of magnitude over other infrared facilities, and this sensitivity as well enables JWST could characterize any named or any numbered asteroid in existence. So I could put in a proposal to observe Stephanie Jarmak if I wanted to, but I probably would have to come up with a compelling reason to do so. And what asteroids have been targeted with JWST? This is just a small selection of those that I'm highlighting here. There have been many different small bodies observed, and not just including asteroids, but comets and trans-Neptunian objects, centaurs and the like. But I highlight a few of these. On the upper left there, it's the Lucy mission, and so that is a mission targeting the Jupiter Trojans, and there was, I think, a couple programs to observe those asteroids in cycles 1 and 2. And then the picture on the upper right there is the asteroid moon Dimorphos, which I have already told you was the target of the DART mission. And then on the lower right there, that is an artist representation of the asteroid 16 Psyche, which will be the focus of the latter half of my talk. And then there's a couple different orbital representations of the asteroids Henrietta and Polana, because they are so woefully unstudied, we don't even have an artist representation of them. But they are the targets of a Cycle 2 JWST program that I am a co-I on, and that's to try to understand the link between these 3-micron hydration features and 6-micron hydration features that I'll talk about a little bit more in terms of applying them to the asteroid Psyche. All right, so why should we care about the asteroid Psyche? So here's the very dramatic poster for the mission. Journey to a Metal World is really their tagline. And that's because one of the formation hypotheses in the current state of Psyche that is hypothesized is that it is this remnant core of a protoplanet. So there was this planet that was forming, it differentiated, and then it is theorized to have encountered this major collision that ended up stripping off all of its mantle and silicate materials, so that you're left with just this hunk of iron nickel primarily, just this intact core. And that theory is based off of some of the featureless spectra that had been observed in the infrared, which is consistent with iron, as well as its very high density, which if it were an iron nickel core, it would need a macroporosity of around 50%. So I'll talk about that a little bit here. So these remnant cores, or these asteroids that have this somewhat featureless spectra in the near infrared through the Tholen taxonomy, they're called the M-class asteroids. It's also based off of their higher albedo, so they're shiny like metal. These M-class asteroids are thought to potentially be the parent bodies of the iron meteorites. So if you go into a museum and you see that big hunk of iron space rock, it may have come from one of these M-class asteroids. And Psyche is considered to be the largest representative of these M-class asteroids, though there have been some conflicting observations of these different objects. So some of these objects also have this 3-micron absorption feature that has been observed on their surface, which is associated with hydration, either due to hydroxyl or H2O water. And these are consistently occurring on some of the larger classified M-class asteroids, whereas the smaller, so like less than 65 kilometers or so, iron or M-class asteroids do not have observations of those 3-micron absorption features. And so there are some hypotheses that state that the iron meteorites came from those smaller iron or M-class asteroids that don't have this hydration, and then we don't really know exactly what's going on with the larger classified M-class asteroids. And so we want to figure out, are they really cores or what's going on there? And so this shows the takeaways in terms of the motivation behind the proposal for that Cycle 1 program, where we wanted to use near spec to be able to assess this 3-micron absorption feature associated with either hydroxyl or H2O water. And you can see the left lower plot there. That was a potential detection of this 3-micron absorption feature on Psyche. But you can see that gray band there. They weren't able to get any data in that wavelength range, which is precisely where you'd want to have data to be able to assess the nature of that 3-micron feature. And that was obtained with the infrared telescope facility. But it suggested there was a feature there, and so we could use JWST's capabilities to better assess it. And then at the time of this proposal as well, there was a new technique to be able to assess widespread molecular water unambiguously from hydroxyl, and that is with this 6 micron emission feature, which is uniquely associated with the H2O bending mode. So the 3 micron absorption feature is associated with the H and O like stretching modes, which either correspond to H2O or OH. And so we wanted to try to see if we could see the 6 micron feature on Psyche. And then we had various potential conclusions based off of the combination of potential results that we would see. And here's what Psyche looked like in terms of its shape model and orientation at the time of these observations. So the near-spec observations took place in early March 2023, and then the MIRI observations took place later in March 2023. And you can see it's nearly pole on, and with an aspect angle of about 23 degrees. And here are some slices of what that data looked like after processing. So like I was mentioning before, how the integral field unit data is kind of like a loaf. This sort of represents a slice, and then we have a 1 arcsecond aperture centered on the photocenter of Psyche, and we drill through that and sum over that to get the 1D spectra of Psyche for near spec G140, 230H, 395H, and also MIRI channel 1, the medium subband, to be able to get the full range of wavelength that we need for assessing these features. And here's the beautiful spectra that we got that covers the full wavelength range we were trying to observe. And these are both with observations with near spec and MIRI. And then this is after we did some near-Earth asteroid thermal modeling and some solar reflectance to get the normalized reflectance of the near spec spectra. And this is what all of our normalized and continuum removed near spec spectra looked like, where the black is observation 1 and the red is observation 2. For near spec, I'll note that the separation and observation time was about half of a rotation period. And you can see there are some like sharp features that show up in one of the observations and not the others in some of these lower wavelength ranges. And that's a unique capability of JWST, and also I don't know what to compare it to because we haven't really had this sort of spectral resolution capability with asteroids before. So we're still trying to figure out what we could compare that to in terms of laboratory observations of meteorites. You can see on the lower left there, you can see the 3 micron broader features, and there's also some around 4.8 or so, which we haven't figured out what that might be yet. But we have characterized the 3 micron feature, and you can see in the left plot there, black and red corresponding to the 2 separate observations, and the blue corresponding to the IRTF data taken from the ground. You can see we're filling out the properties of that 3 micron feature quite nicely. And the ground-based data, they interpreted this feature as a sharp feature, but when we did some comparisons to other meteorites and asteroids, we thought it was really ambiguous whether it was sharp or not, and could be actually rounded. It's not really clear what that shape is. And then for MIRI, we did not detect a 6 micron feature. We can only put an upper limit of around 39 parts per million on any H2O that may or may not be present. And actually, in the first iteration of our analysis, when we were using one of the earlier versions of the pipeline, we did see a 6 micron feature of 1%, which was consistent with what had been observed on the moon. So we were like, great, we saw it, and then we ran it again through the pipeline, and there was nothing there. So just as a cautionary tale, make sure that you are, using the most updated version of the JWST pipeline. So what does this mean? So we are still trying to figure that out, essentially. So we don't observe H2O on Psyche, but we do observe this 3 micron feature, and so we are pretty confident that there's some sort of hydroxyl on the surface of Psyche. But how that hydroxyl came to get there is still an area of active research in terms of being able to compare that to other studies of asteroids. So the hydroxyl could potentially have been implanted by hydrogen ions from solar wind implantation, or it could be impacts from hydrated carbonaceous asteroids. There are several explanations from an exogenic, so an outside source of this hydration, and then there's also, this is still consistent with Psyche potentially being more of an enstatite type asteroid or P-type asteroid, which would indicate that it had formed further out in the solar system and then migrated inwards and wouldn't represent a solid metallic core. And this could also suggest that instead of a solid metallic core, Psyche is this sort of catastrophically fully disrupted object that had a high content of metal and then re-accreted into this sort of rubble pile. There's a mix of silicate and iron material. And then that's a QR code for my paper if you're interested in checking it out. And thank you for your time.
Thanks so much. So questions? Okay, then I'll start with one. So you showed animation of the shape of the Psyche. So how, like, what is the data you're using to reconstruct this shape information?
So there had been radar observations with, I believe, Arecibo of the asteroid Psyche, and then one of my collaborators on the project, they put it through some fancy Python code to be able to reconfigure and create this shape model. So the one on the left is the most up-to-date shape model, and the one on the right is just whatever random version is used in this really valuable tool called ISAM that is able to tell you the orientation of the asteroid at any time of observation.
Okay.
Yeah, I'm just wondering how long the observations were. So what's the prospect of getting a lot more computer data?
Yeah, so the observation times are very short, but then the concern is like the overhead cost in time. So I'm working on a cycle 4 one right now, and it's less than an hour of, say, science time, but it ends up being like, 8 to 12 hours of JWST time or something. I think so it was 12 hours of JWST time for this cycle 1, which had 2 visits, but the one I'm working on is more for 1 visit, so I think it's more like 5 hours. But it's pretty significant in terms of JWST time because of all the overhead that goes into that. But the actual exposure times are really short, especially for Psyche, because it is quite bright. Actually, that's one of the issues that we have with this asteroid is because it saturates in a lot of the channels in MIRI. And Catherine DeClear, she has a cycle 2 program that's partially completed now to observe the smaller M-class asteroids, and she chose the smaller ones because she could observe them in all of the different channels with MIRI. Though we do technically have channels 1 through 4 of the asteroid Psyche, because the way JWST MIRI works is if you're getting 1 channel subband, you get all of them. So the MIRI advisor that I had that was assigned to me said, why don't we just add all of these? So we technically have them, though Psyche saturated, and some colleagues are working to try to get useful information out of the saturated data.
In this asteroids with high metal content, is it in principle possible to expect some kind of magnetic signal?
Yeah, so there's a magnetometer on board the Psyche spacecraft, and so that's going to be able to detect the presence of any potential magnetic field that could be produced. And then also the distribution of hydroxyl across the surface of Psyche could be indicative of the configuration of a potential magnetic field, because it would redistribute the solar wind as it encounters the asteroid. So I'm hoping with future observations, even with JWST before Psyche gets there, we could also have a better understanding of whether a magnetic field is present and what it's doing.
I'm curious about all the extra setup time for JWST. Is it mostly because you're tracking moving objects? Is it because it's fairly very small in area, or you don't have any idea what the problems are?
No, yeah, I have no idea why it takes so much time. There's some amount that it's slewing and setting up and scheduling buffer and things like that. But I'm not sure if it has to do with how fast it's moving to do target acquisition and things like that. I'm sure all of it just adds up.
I wonder if the density measurement is wrong. If it isn't really a super dense area. You mentioned something about a macro porosity, so it's not huge.
Right, yeah. That's a consideration too, which the Psyche spacecraft will be able to get more refined information about the density. But I think, I'm not sure if I mentioned it in this talk, but even this like macro porosity, the macro porosity that would be needed if it was mostly iron nickel, it would have to basically have been catastrophically disrupted, which would have produced an observable family that has not been discovered. So that's just another sort of reason why it's iffy to consider that it's a sort of intact core.
So is the mostly metal partly from the radar measurements and radio reflectivity or reflective?
So the consideration of it being mostly metallic comes from observations in the visible to near infrared showing a relatively featureless spectra, which is consistent with iron, as well as in the UV, and from the very high radar albedo and the high density. So all of those together have sort of, that ends up being what classifies the asteroid as an M class, though there are some potential overlaps and consistencies with other asteroid classes like the N-types.
I'm just thinking because on Venus, the radar measurements gave a lot of metallic reflections, and they assumed that it was a very metallic surface, but in fact it's really just a high metal contact minerals. So they're dense, they have a lot of iron in them, and that's causing the reflective surface.
Yeah, there have been some laboratory studies that suggest just adding 10% iron to a material can cause it to be this same sort of featureless spectra. And then we know from just any remote sensing from telescopes compared to in situ measurements from spacecraft, there are going to be discrepancies, and it'll be exciting to see what Psyche spacecraft sees there.
Other questions? Okay. This question one.
Okay, the question says, did you consider larger molecules with hydroxylation, like amide-containing molecules? I'm not sure what amide-containing molecules are, so I'll say no to that question. But yeah, there are many other, so there are lots of different interpretations. I think tholite or something like that, and structural OH in minerals are other considerations, phyllosilicates, and then there's several potential organics that could be observable in the longer wavelength ranges if we're able to get some of those values from the saturated data. But yeah, there's another potential hypothesis for why Psyche is so bright, and that could be in the form of salts on the surface. And so I'm not sure what features those would correspond to, but that could be another interesting avenue to try to distinguish between the two hypotheses.
Any other questions? Okay, if not, let's thank both of the speakers.